this part of the tutorial actually. It's this we're just doing this part, inversion of surface wave dispersion and receiver functions for the structure. Okay, there is an introduction, and the whole tutorial package uh, is contained in this table. So then you can zip, you do some machine processing, changing, and then the main point is here. So we're inverting for the inversion of surface data. It says can lead to velocity models that fits the observed data, and which can also be an unrealistic F model. So you have to know this with all your inversion uh, process. So problems. So you have to really, after getting the results, it's a really good thing to really try to analyze the results and see if you are getting an unrealistic or realistic model. And also, what helps is to know a bit of the geology. At least that helps, so you can associate some high or low velocities to probably some tectonic or geological structures within your study area. Okay, so we first will go ahead and see how we use the dispersion curves to retrieve the velocity model, the velocity structure. So this is the results of. So let's go to the uh, to this. So I've already downloaded this up. I'm just going to go ahead and open it up. I think it's the SVF, probably. Okay, so this generates, if you untire this, it gives you three directories. This one it contains the surface wave inversion. This is a receiver function inversion, and this is the joint inversion of surface wave and receiver function. So we can combine the two data sets, the receiver functions and the surface wave, to constrain better the velocity model. We'll see that. Uh, so we're going to do the surface wave. So just like this is the surface wave. So it says just cd into this directory and do do it. Let's look at what it is. So here it gives some indication. So if you read the manual, it gives you the parameterization actually. Let me see if it's somewhere. Yeah, I think this is the starting model. How do I know? Okay. Yeah, so this is your starting model, okay? This is the initial model you give. So in this case, I think there is should be 95, so about 80, say 78 parameterization. So what it means is that there is 88, oh, no, like this is the different, what it means is, your structure has been parameterized. So this is the depth, and each one. So the first layer is 2 kilometers, and the VP is giving us 8. The VS is giving us 4. So you can see that the VP, VS, and the thickness for all the at least up to the first 20 layers. I don't actually know. I am not counting the actual layers, but 15 or so parameterized layers. It has the same velocity and same thickness. So we're defining some same 2 kilometer, 2 kilometer, 2 kilometer layer. And then as we go deeper, we lose our resolution. So then the thickness of the layers increases a bit. And then we increase the thickness to 5 kilometers. But then the velocity is still constant. So this is just the initial model. And then later, at a much deeper depth, the thickness goes to 10 kilometers, okay? So the maximum depth, to find the maximum depth, you have to add up all these layer thicknesses, and then that gives you the maximum depth. And yeah, so then it goes 10 kilometers to the base of the model. So this is our starting model. And then what the inversion is saying is that, so, okay, so now it gives you some documentation, says the first 50 kilometer boundary is index 25. And then the remaining 100 kilometers with 35 and everything. So here, these are surface 96. If you see in here, this program, this is actually the program that does the inversion. Okay, so all the inversion procedure that we looked at yesterday, depending on which method you choose, it's been carried out by this program. And so that's the calling program. Is this okay? So that's the calling program, and it gives you the layers from, I think it constrains the layer 35 to 40. So then I think this is just the layer numbers. Okay, this is some parameter that the program takes. You can see that if you, okay, let's go into self attainment way. We can see what each one means. I mean, if you read the documentation, you see it, but we can call no, the help is not working. Oh, okay, strange. No, okay, then should just look at the documentation, because most of the time you call the help function and it will indicate for you what these different parameters means. But I think here it's just for the inversion. So then these are the layer, and then this is the constraint. So what it means is that sorry, here it's sorry, this 0 point, this value between 0 to 1 is an indication of how much we want to change the layer velocity. Okay, so if we look, what it means is that if the first layer it's up to 25, it means all this, say the first 25 parameterization, we allow the inversion to really change the velocities. Okay, and so that's why it's closer to 1. And once we get deeper, we decrease the parameterization. Because why? Because our data is not sensitive. So if the inversion try to fit it too much, it's going to give us some wrong results, which is I think it's written somewhere here. Okay, so inversion techniques, the difficulty arises because the data sets have limited resolution. Okay, so for the surface waves, there is inability to define sharp discontinuities that I think I mentioned in the morning section, and the sensitivity decreases with deeper structures. So then you don't want your inversion to try to fit the deeper structures. So you mainly focus on changing the model parameters of the shallow structures. So that's what this part means. And so especially if you go much deeper, then you don't really change the model velocities at all. Okay, so that's that part. And then this is the crustal bit. So this is the crustal part. So this is the first layer, second layer, up to the ninth layer. So we allow the inversion to change it strongly, and then again here. So yeah, and this is basically it. And then you just generate some model. This is the end model. So this is it. Yeah, I mean, it becomes clearer if you read the documentation, the actual documentation, but we don't have the time to go through it. And you normally get used to this when you work on it a lot. So now I just does this iterative thing to really to change the model. So I think it's finished, and now it gives some output. And now we have to show, how do I show this up? Okay, this is the plot one. So, okay, I think I remember the whole thing. How do I plot these models? Okay. Now let's plot one of these. Okay, ESPN. So I want, because now it finished the inversion, I want to show you the results. This is the output of the code. I think it's somewhere here. Let me see where it does the output 45 and model. No, it doesn't say that here. Okay, just let's see that first. Okay, so now we get figure one. Figure. Okay, I think it should be figure one, but anyway, and then we can see. Okay, so this is it. Wait, no, there is something that I wanted to say before. Right. Because I wanted to show you the how the data is inputted, the dispersion curves actually. Now it's so, everything is so dirty. Usually it's in this file. No, this is some parameters. This gives you the starting model and the dispersion curves. Yeah, so this is the name of the dispersion curve folder, and oh, okay. I wanted to show you, to explain this to you. Where is N? Okay. Okay, good. So once we get the dispersion curves, how I should have done this before. Wait, let me see if I can recall some of the morning data. Okay, so you in the morning, the dispersion curve that we picked up, okay, the group velocities and everything. This is the data that it gives. When you remember, we clicked save and everything, so it saves the dispersion curves as this. So this is the name of the surface wave program. This R means it's Rayleigh wave. This X, this U means, I think this is the group velocity, and when it's C, it's phase velocity. When this is L, is love waves, and I think this O means it's fundamental. This is the fundamental mode. Okay, and this is then the period. This column indicates the period, and this is the velocity. Okay, and then this is some I think this is the standard deviation or something. So once you have it, once you save your dispersion curves in this form, then you can transfer it to a file, and you give this file as the dispersion curve input. Okay, so here you can see the same thing, but it's Rayleigh wave, but it's C. So this is the phase velocity. This shows the fundamental mode. This is the period, and then this is the velocity, and this is some statistics. And so this is all the data. So from the groove velocity, sorry, this is phase, and then you see it changes to groove velocities. So you give all your dispersion curve information here, and then phase velocities, and so the program just read it line by line and see that okay, it's phase velocity, and sorry, it's Rayleigh wave, it's phase velocity, and it's fundamental mode, and try to process these data. So all these data is what we see plotted here, along these lines. Oh, what happened? No. Yeah, so this is the data, and this is the fit. This is the dispersion curve. So you remember our starting model was one straight line for the VS, I think 4.48. So this is the straight line, and this data, all these black and triangle data points are the scatter plots of the data. Change this model such that this Earth velocity structure reproduces, gives this fit, which is the best fit for the data. Okay, and then the point is this model realistic? Does it explains a really realistic Earth model? Are we expecting the velocity jump at around 5 or 5.8? Then this is the analysis you have to make, and also make some statistics in your inversion to see if what you're getting it's a correct results. Okay, so these are some things you do, and yeah, and I think these are the sensitivity kernels of how the models are changing. So that's the part for surface waves. It says, okay, we can show the progress of the inversion. So here, I think, let me try and see to do this. So we have show, okay, let me put this down so I can see the command.
I have a question.
Yeah, sure.
So when we were generating these models, the program generated some values where we had the thickness of the layers. So I noticed the thickness were increasing as we were going deeper. So when we have, maybe assuming we have maybe a sandwich layer where like that layer is thin and is sandwiched between some two layers, and those values which are being generated doesn't fit, like it will not be able to like tell us about the sandwich layer or what.
Okay, so that's a good question. The point is, our layer thickness is actually, it's not a model parameter this time. It's an auxiliary information. We are fixing the layer thickness. Okay, so where is this? Okay, that's why you try to make the shallow part of your structure, and you have to parameterize them in a much more thinner layers, not bigger ones, because then in this case we allow just small changes in the velocities. Okay, and then the deeper part is much more thicker. Okay, so this inversion doesn't change the layer thickness in this case. So let's say if this is a velocity inversion, a velocity decrease. So we have some layers, and this is a velocity, in this part there will be a velocity decrease. Then, or let's say even the whole thing, then just this 2-kilometer thick layer will be changed. Okay, if it's much more if the structure that is causing this low velocity is say 10 kilometers, then it will change 5 of this. Okay, so it will change the whole 5 layers to make that to sum up to the 10 kilometers. Okay, if it's only 4, then it changes 2 of them.
Okay.
Okay, so this is it. If it's bigger, then it adds a lot of the layers together and then present that as one block. Okay.
Okay.
Yeah,
Okay.
so that's why usually you don't say so in this case, if let's say we start our surface layer thickness parameterization by 5 kilometers, and now there is only there is in reality there is a 2 kilometer velocity decrease here, then either the inversion is going to change this whole 5 kilometers as a negative velocity anomaly, or it's going to just overlook this 2 kilometers and just give a positive velocity anomaly. Okay, so but
Okay.
if you parameterize it in such a way that the layer thicknesses are small, then the inversion is free to change just this 2 kilometer part as a negative anomaly, whilst these are positive ones.
Okay.
Okay, that's
Okay.
why you start the parameterization. You make the parameterization at least in the shallow part where there is a lot of variabilities, where the structure changes a lot. The layer thicknesses are thin, and then once we get deeper where we have a smooth velocity structure, then we can allow for a much more thicker layers. Okay, this is how you do the parameterization.
Okay. Thank you.
Yeah, good question. Okay, so then, okay, so I wanted to show this, and then temp, and then the end model. So what it means is that this thing just shows the models, like plots all these models. So all these temporary models are just the iterations, okay? And then, so this is the starting model, the one, the uniform velocity. Okay, I'll show that. This is the starting model. And then the inversion changes the model, step by step so smoothly until it gets to a final model, which is the end one, the deep blue one. Okay, so you can see that also by when I run this, and then again, I think, let me list to see what's the name of the output. So the output will be show model, this one. Okay, and then I can plot that. So I plot. And I give the name figure 2, and then it should be there. Why is this figure 2? Why do I suffer? No, I'm in the wrong directory, sorry. Okay. Okay, so this is the starting model, which is the uniform 4.4, and then the inversion changes it. So I think that initially it just say, okay, probably this is the velocity, and this is the velocity. Then it changes it this, and then that until the fit is very well. So all these are models, different models, fit the data in some capacity. Okay. But so this is why you have to investigate your results well. But this is then the end, the final model is the one in blue. So then this will be our structure. Okay, you can see that now the layer thicknesses are increasing here. Okay, so the changes here are much more uniform. And in this cases, the layer thicknesses are smaller. Okay, so it allows for just a small changes in there. Okay, so that's how you use the surface waves, your dispersion curves to generate your Earth model. And there are a lot of things. You can also change the data and practice with this. So now the next one is to use the receiver functions. So you remember the receiver functions, how it looks like this time series with these forces. So the point is to try to get an Earth model that reproduces this time series, these forces on the time series. So you give, again, you also give an initial model, and then using the data, you solve the inverse problem, okay? So it's fairly straightforward once you have these codes and everything. But sometimes you have to write your own codes. That's where you have to use all the mathematics and everything. And so let's go, receiver functions. Okay, so now in this case, the data is actually there. We can have a look at them, as at least some, not everything. So let's say if we look at this one, this is the radial component. If we plot, so this is the receiver functions. Okay, so once you finish with your processing, this is the output, and you put them in this folder. So we're in receiver functions. I think the results should be. Okay, so this is your starting model. So these are some inputs for the receiver function code. This is the RFTN. 96 is the code that does the receiver function inversion. And so the RFTN list. So this is our input data listed here. So we have so we're just inverting for the radial component of the receiver function, okay? And we are using these different frequency bands, so 1.1 and 2.5. So we're trying to fit the low velocity, low signals, and also the high signals, which is given by the alpha. And what again to say about this? Okay, let's look at the starting model. Okay, so it's a similar starting model, and I don't know if I said this in the afternoon. Depending on the program you use, how you parameterize your models can be different. Okay, so you just have to read the documentation. This is not the only program that does receiver functions. There is also a lot of Python based programs that does receiver function computations now. I think I'll just open one of them and we'll see how it is. So this is the same, almost the same parameterization with this, it's parameterization for the initial model. And yeah, so let's go ahead and just run this up and see. So where is the, okay. Yeah, this takes a bit of time. I don't know, for some reason my computer is so slow. So yeah. So then it does this iteration and it shows you the final model. So let's see here. In the meantime, if you look at I think these are the same stations. If you look at the model for, okay, I think it's in the final part, we can discuss that. Now the code is running, it will take some time. So I don't know, let's see, receiver functions. Boy. I think there is now a lot of Python OTS5 programs that also does receiver functions. I mean, like, it's not only this code that does receiver function processing, pre-processing and inversion. You can find a lot now on the internet. So these are Python packages actually. These ones, the one I'm running now, that I asked you to download, are much more Fortran based. These ones are Python based. So it's the same thing. It gives you some, this is just the method and the documentation. So installation, the things you need to do, using, okay, the model and how to run everything, and the header informations like the metadata you need. So yeah, there's a whole lot of programs out there that you can you can use. And also even with the inversion, this is much more of a linear inversion, or I mean linearized inversion. There is also some non-linear ones, I think, that you can find out there. And there is also, I think there is a tutorial. Okay, there is a tutorial here. I think there is a notebook that you can open up and see. Okay, so running. So calculating receiver functions from minimal examples. Okay, so you call some Python modulus, and I think so. This is just some packages, so you have to download the whole package. So the same thing, you have your signal, and you do the pre-processing, you remove the instrumental response, and then you deconvolve, and then you have your time receiver functions time series. This is it's a fairly straightforward procedure. And then this does, okay, this is the same thing. So first, of course, first you have to download your events, okay? You have to download your earthquakes. And usually the earthquakes, you use the ones in the distance, or the distance ranges are, let's say, 20, 30, or 25 degrees to say 90, or in some cases 100 degrees. So you these that's the epicentral distances you use for earthquakes that you want to use for receiver function analysis. And so you download these events, and yeah, and then basically you just do the same pre-processing. And then, because now, let's say if you have a station here, located here, you can have events all around, so different azimuths. And so you can plot your receiver functions as a function of azimuth, so you can see how it changes. Okay, and these are the back azimuth plots, and then it gives you, it kind of seems like a seismic waveform thing. And these are something, so you can have all these plots. But then these are just first order information, so you still need to do the inversion to get the structure. Okay, I think it's finished. So these are some, they are also the point is there are some Python packages that you can look at once you're interested to do some receiver function works. And okay, so the structure, and let's look at that. What's the name of this output? So it's RFT and PV. RFT and PV. Okay, this one. So that's the output. Okay, so now this is the results. And so this is the starting model. The blue line is the initial model, the starting model, and this is the velocity structure that we retrieve. Now the red line, the red waveform is the receiver functions coming from this, using this Earth model. Okay, so we can see that we can fit better this initial peak, but this peak is we cannot fit this peak, so a peak here, and we do okay here, but also we underestimate this peak. And then you can see how well each this Earth model reproduces all these waveforms. In some cases it fits well, in some cases it doesn't fit well, but this is understandable. You cannot get a best fit, I mean like a perfect fit like we discussed yesterday. So this is the results for the receiver functions, and you can do that. And also you can show I'm not going to run that, you can show the progress of the of how the initial model was iterated to get the final model. Okay, so here we see there's that the interfaces, the discontinuities are much more pronounced than we saw in the in the using the dispersion curves. Okay, so because receiver function has good constraint on the interface locations, sorry. Yeah, so that's just using the receiver functions. And we can use both the receiver functions and the surface wave dispersion curves to retrieve the S structure. So that's called a joint inversion, and it's the same similar idea of using, say, gravity and seismic waves to constrain the S structure. So it's the same mathematics problem we're solving. So then that is in the folder joint. Okay. So here we have the joint. So in this case, you have to give the receiver functions and then the dispersion curves. Okay, so this is the dispersion curve data, and this is the receiver functions for saying RFT and list. And this is the receiver function data. So now we have both data and the starting model. No, shouldn't have opened it that way. And okay, the starting model is the same as the one we have already seen. Yeah, one starting model, and then so just let's go ahead and run this. So you go into that. Once you provide your input files, you just go ahead and run the do it. Oh, let's see what's in the do it. I didn't open that yet. Okay, display. So it's now it's calling the joint. You see each one has a different program that does the inversion. So this is a joint inversion, and I think this is also the iteration, how you change the parameters, the parameterization, the velocities of the layers, and yeah, not much to it. And then plotting and resolution kernels, and then some outputs. I mean, to find more, to get more in-depth understanding of these programs, you have to read the documentations. I said that in the morning to understand what is actually happening. Okay, so if you run that, okay, this is also going to take some time, just like that one. Okay, so in this case, it's just going to fit the data. So the joint inversion is trying to fit the dispersion curves, and at the same time fit also the receiver functions. Okay, so in this case, it's in the single inversion case, it's only trying to fit the receiver functions. So in this case, it's just fitting both data. That's just the idea. And if we, because it's going to take some time, so let's just discuss this. If we look at the final results, so here you can compare the results from the three inversion methods. So because the stations are the same, so we can see the structures, we can compare the results we're getting for both structures. So the red one is the initial starting model. The yellow green is the joint inversion, the results we get from the joint inversion of the receiver functions and the surface wave signal. And the green line, yeah, it's the receiver functions, and then the surface wave is the blue one. So you see that here in most of the cases, the surface waves gives a low, almost, no, not almost of them, at least. Okay, the receiver functions, that one is prominent. It's giving a high velocity. Okay, in almost all the cases, you see it's leading here. This is the receiver functions. It's leading always. And then the the surface wave signal is this one. So it's behind the receiver functions, but at least around 40 kilometers. So you remember our model that we used to generate it was like 40 kilometers, like a 40-kilometer layer over half space. It seems that there is a jump in the velocity around this depth. So the velocity increases here, and then it decreases again, and then tailors off. Okay, at 80 kilometers, it's almost no difference between the three. And then the joint inversion now tries to give a much better fit. And here there is the velocity is around 4.3, whilst the receiver functions, the velocity is around 4.8. Okay, and the surface waves are around 4.3. So in practice, what you have to the thing you have to note that in practice is that surface waves, using the surface wave dispersion, you can really constrain well the velocities, okay, of each layer, but not so much the discontinuities, okay. And the power of the receiver functions comes from constraining the discontinuities, because you know the PS conversion is at the interfaces. So if you use only the receiver functions, it's likely that you can really map your discontinuities, okay, your layer boundaries, but your velocity is very shaky. It gives us acceptable velocities, but not the best. Whilst the surface wave will give you a very good velocity estimate, but of course it's difficult to constrain interfaces. Using both the receiver functions and the surface wave dispersion curves kind of gives you an in-between, a middle ground between these two, how do you call it, advantages. So you can constrain well the velocities and some interfaces, that some discontinuities in the subsurface. So that's why we do this joint inversion to really have a constraint on the velocity and also the interface. So that's it for the inversion. This is the end of the discussion for the inversion of the surface wave and everything to get the velocity model. So yeah, I think that's what I wanted to do now, at least for now. And there is also some other examples that you can run through. And yeah, any questions? No? Everything is clear? Or you don't understand? Or it's still running? Damn.
We'll go through, and when you have any question, we will let you know.
Okay, yeah, sure. Yeah, I mean, it's important you download the program and install, because this was supposed to be you guys running and just me looking at what is coming out and discussing. Yeah, my computer takes a lot of time. Okay, in the meanwhile, we can. Okay, so this is done. I already explained the results anyway. Let's try and finish this up, because yesterday it was. We have some 30 minutes left, and okay. Yeah, so Okay, now let me bring this up first before let's refresh. Where is this measure of length? Okay. So you remember we were talking about linearizing a nonlinear problem where the procedure is to start with a starting model, predict the data, and then find the misfit vector, and then use partial derivatives to form the G matrix, and then you try and solve for the delta M, that's the misfit, the weight, the perturbation you have to add to the starting model to improve it, and then you do some iterative thing. Okay, so we didn't see an example of that. Let's look at an example of that today. So let's say you're given a model. So this is just one equation, okay, a system with one equation. So now this is the model parameter is raised to the cube power. So it's really highly nonlinear. And you then have to form the G. This is how you form the G matrix. So you find the partial derivative. So this is only one M. So then this equation, so it's actually a derivative. So with respect to M will be 6mi, okay, if there are more I, so to the power 2. And so this is the G. And then if we have a start, we pick our starting model. So now our G is given by so our G now is a function that we need to evaluate, okay, each time we have a model. So now if we start, so this is our equation, this is our model, this is the relationship to compute G. And then we start with a starting model, and then we evaluate G at the starting model. So that will be, it's 1, so G is now 6. And now we use G to predict the changes, to predict the data. So we get 2, and we form the misfit vector, okay, which is D minus D predicted. So that's 16 and minus 2, and that's 14. And you then, so now you have your delta C, and this is just to find the length. So you square it to find the total misfit. And then you find the delta M1 by solving the problem, the void problem. Delta C equals to G delta M, okay? So our G is 6, and now delta C is 14. So we find a delta M. And once we find delta M, we add, we perturb our initial model by delta M. Okay, so this is 1 plus, this is delta M. Then this will be our best next model. Okay, so like we are doing an iteration, so this is our next model. So we now use M1 as the starting model, and we can go on with the iteration. So this is step 1, and now you use M1, so you put M1 in there, and then your G now changes to 66. Then you form the how do you call it, the predicted data, and you form the misfit. Again, you compute the total misfit, then you estimate delta M again, and then you form delta M2, and then you go on. So you do iteration number 3, you compute again. So G is changing, then you find your delta C, and then you continue till your misfit there's the misfit between the predicted and the observed data is zero, or the number of iteration is max, you reach the maximum number of iteration. Okay, so that's it. This is how you go through it. So it's just once you set up the initial first step, it's just an iteration of just start giving the changing the starting model, so that you just go through the loop until you fit the data well. So let's say this is what I wanted you to write. So I want you to write a program, okay, based on the steps, five steps. So to find the location of an earthquake, okay, given some model parameters. So this is the equation that defines the arrival time for an earthquake in some location. So I think the station, so for different stations, so the earthquake location is at X, Y, Z. Okay, so this is the earthquake parameters, S, Y, Z. And then the stations are given by the X, Y with the I subscripts. And then it's 1 over the velocity. Okay, so distance over time, distance over velocity, plus this is the origin time of the earthquake. So this will be your model. And then now if we want to form the G matrix, we have to, now we have we have 5 parameters. So we have V, we can input V as a model parameter, like we don't know this, so we can ask our inversion to search for the velocity of the medium and to find the location of the earthquake. So the location will be X, Y, Z. So this is 3. So 1 plus 3, that will be 4. And the origin time can be cast also as an unknown. Okay, and that will be 5. If we say, okay, the origin time is 0, then we have only 4 model parameters. And then if we say, okay, we assume some velocity, then the velocity also falls out, and so we will have only 3 model parameters. That will be just the location of the coordinates of the earthquake. Okay, so in this case you find, so let's say if we want to compute the G matrix, then it's let's say if we just, here it just shows you the partial derivatives with respect to X, which is the earthquake location. So then this will be, so we're trying to find a partial derivative for this equation with respect to X. So the X only occurs here, and it's to the power 2, but it's also to the square root. Okay, so it comes, you just do this computation and the X comes out, and then I think that 2 in here cancels the 2 from the square root, and then this will be your results. And then you do again for Y, you do for X, for Z. Okay, so in this case, say you have G with respect to X, G with respect to Y, G with respect to Z. And then for the next equation, that's the next station. Okay, you also have G the same. Okay, so that's why this is 1. So that's the first station. So the relationship between the first station, station 1, and the event, and then this is station 2. Okay, so and then that yeah, Y2 and Y. If let's say the medium velocity is also an unknown, then that one also comes in. Okay, V1 and that. And so that's how you form the G matrix. And this, I think, is the partial derivative with respect to origin time. So if we find the partial derivative with t, then it's just 1 because the t doesn't multiply this part. So all this part goes to 0. And then this part is just a constant. Okay, so then this is it. So this goes into your G, and then you form it. And then once you have the location of the stations, you put that in there, and you try to invert for the model parameters, which are this, that, and maybe the velocity. Okay. So try to write this, and then we see. If you have any problem, I'll be here the whole weekend. Then you can send me a message. We can discuss that. I'll later I'll give you the codes, and then the actual what I wrote myself. So these are the parameters of the earthquake. So what we're doing now is to first, because we have to generate some data. So we are generating some synthetic data just like we did. So we give some actual parameters of the earthquake, and we use this relationship to generate some arrival times at different stations. So this is the station location. So this is X, this is Y, and Z is 0 for all the stations. Okay. So we use this to derive some data using for each station. So I is for each station. And then we try to use that data and use the inverse procedure to try and see if we can estimate these model parameters. Okay, that's just it. It's just some exercise. So these are some hints. So your X, you can put your X, Y coordinates into some vector, and then you have your station data, and then you compute your forward model, use this model, and then you store it in as the data. So that's the observed data. And then you use, you use a loop to make for each station the observed data. And is that it? No, shouldn't be. Okay, yeah, there's another one. Yeah. And then you pick your, now after, so once you generate your, you do the forward computation to generate your data, then you try to use the inverse procedure to try and see if you can recover these model parameters. Okay. And so you pick a starting model, you calculate, you predict the data, and then form the mixed fit, the same thing. So these are just vectors, operations. Then you form your G matrix. So your G matrix will also use a loop to compute it. And then you solve for delta M, and you update your model, and then you do the whole cycle again. Okay. So your new model will now go into your starting model here, and you predict the data again, and you do again, and you go again until you reach some maximum number of iterations. So you fit your data. But now keep in mind that there is no errors in this data. So your fit should be really, really close to the actual model parameters that that you used. And then we see. Try and write this, and you can send to me by Friday. If you cannot write it, just also just send me something that you just wrote so we can discuss. Okay, it's not any hard line deadline, but so we can discuss the results individually. It doesn't have to be the whole class. Okay, so I can get time for, you guys are just 6, so for me it's okay. Okay, we can just fix some time where within the next week that you're free, and then we go through this thing, your code, and then I give you some other hints on how to go about this. Okay, I think that's that, and yeah, I'm done for today.
Thank you.
Any questions, please? Hello?
Hi.
Yeah, okay, so that's it for today. Any questions? No? Okay, so yeah, please try and use the remaining time to try and install the program and go through it, okay, because you didn't practice yourself. So go through it like you said, and let me know tomorrow what happened, okay? So don't go and sleep yet. Use the sleep with like 25 minutes of the time. Download the program, try and install it. If you have problems with the installation, then we can discuss that tomorrow too. And try and repeat the exercise, and then tomorrow you give me feedback. Okay, so use the remaining time to do this, please. Okay. Okay, so I'll see you guys tomorrow.
Okay. Bye.
Okay, bye.
Bye.
Morning.
Hey.
Yeah, I'll come on WhatsApp. I want to call you on WhatsApp.
Okay.
So
Sure.
yeah, so Innocent Kumsa Tarek. Say so tomorrow, right?
Yeah.
Yeah. I hope you prepare for the exam. It's too much. I'm going crazy. It's too much. No. So tomorrow, okay?
Yeah.
Bye-bye. Bye.
Bye.